Welcome to the University of New South Wales and the School of Mathematics and Statistics. My name is Thomas Britz and I'll be looking at this problem here, problem 39 from topic 5, which is all about graph theory of the course Discrete Mathematics or MATH1081. In this problem, we're going to look at a graph, this graph in fact, and we're interested in spanning trees that are minimal in some sort of sense. Actually, we'll be looking at two types of minimal spanning trees, the minimal spanning trees and a variation of that. So what do I mean about minimal? Well, we have some green numbers here, and they are weights that we associate to each of the lines here, or the edges here, and we add all them together and we get some number. Now if you do that for this graph, you get 4 plus 4 plus 4 plus 1 plus 1 plus 1, etc. You get some number. Now you can do the same thing for subgraphs as well. Take all of the edges in whatever subgraph you have, in this case a spanning tree, and you get a bunch of numbers that you add together, and that gives you a total weight. And if that weight is minimal among all the spanning trees that you're looking at, then we have a minimal spanning tree. Now, as I said, there were two ways of interpreting this minimality. There's the usual minimal spanning tree, which we could write just like this. And then there's also another variation which I'll get to. And to illustrate those two concepts, let's suppose that this graph, it gives an overhead view, for instance, of a little town out back where they only have gravel roads, for instance. They've got 1, 2, 3, 4, 5, 6, 7, 8 different locations, houses and the town centre there maybe. And there are gravel roads between them, for instance a gravel road here along that edge and that edge. So in other words, these edges represent the gravel roads. But the townspeople would like to upgrade their road system by replacing some of these gravel roads with bike paths, nicely paved bike paths, so that they can get from A to B and in fact to all of the other letters with ease. So they don't have a lot of money, so they want to do it as cheaply as possible. So these numbers here could be the costs or possibly the number of kilometres or whatever, but they want to do it, they want to find some subset of these roads. They don't want to do all of them, but in such a way that they can get from any one of these locations to any other of these locations. Now, they will use a minimal spanning tree. They use a tree, they'll use a spanning tree, because they want to get from every point to every other point. So our subgraph, which denotes the edges where we'll be upgrading our roads, that has to be spanning. And it's a tree because we don't want cycles. If we have a cycle, then we could have dropped one of the edges and saved a bit on cost. And it's minimal because we want to find a spanning tree with lowest cost or lowest number of kilometres or whatever. Now, that's sort of a global sense of minimal spanning trees, or as we say, just minimal spanning trees. There is another slightly more local way of seeing it, and that could be the mayor of the little town. He or she might live there, for instance, or maybe in A, let's say, and he or she might not be interested in the total cost being minimal. They might more be interested in the roads being most accessible from where they live. So they want to get from A to all of the other places, spending the least amount of transport if these numbers were kilometres. Then you have a variation of this minimality, which is the minimality relative to A. So in other words, the distances from A are minimal. So, but that might mean that the total cost goes up because we're making special considerations for A. The first thing that we need to do is to find a minimal spanning tree. So we need to find a spanning tree in this graph whose sum of edge weights is minimal among all spanning trees. Now the way to do that is really simple, and it is pretty much what you'd guess. we just start off by being really, really greedy and take, well, if we want it to be minimal, the spanning tree, we just take the edges of minimal weight, like the 1s here maybe, and the 2s, 3s, etc. And we do that in such a way that we don't choose any cycles. So we just choose edges as we want, and whenever we might choose an edge with a cycle, then we ignore it. Well, super simple. This is called the greedy algorithm, or Kruskal's algorithm, because it was Kruskal that discovered it in 1956, I believe. What I've done here is write up a table that can help us do that. So what I've found is the edges with lowest weight, and I've just written them down, and I've written them down in just some random order. So you can write them up, you can permute these in a different order if you want, and the algorithm will still work, but it might give you a different spanning tree. Okay, so what we're going to do is we're just going to say, well, do I want to choose this one? Sure. Do I want to choose this one? Sure. And I'm going to choose these weights going down the list as long as I don't run into any problems of the sort that I get a circuit or a cycle. So let's have a look. The first edge, of course, won't give us a cycle, so we can say yes, let's choose this. So that was A to B. We choose this edge there. A to D is here, we can choose that, yes. B to D, now we've chosen A to B and A to D. Now if we choose B to D, then we have the we'd have a red triangle here. So we can't do that, so we can't choose B to D. So we write no here, and then we go on. D to F, where's that? Here it is, D to F, yes, we can add that, and there won't be any cycles, that's fine. So yes. What about D to G? Yep, we can add that one as well. Yes. F to G, no, we can't do that, because if we added this edge here, then we'd have this triangle here, this 3 cycle here. So we have to unfortunately decline that choice. But what about the next one? And D to H. D to H goes there, yep, that's perfectly fine. G to H. Where was G to H? No, we can't choose that one either, because that would create a red triangle here, or 3 cycle there. So unfortunately not this one. Now we're into the edges of weight 4. A to C. We can choose that one. What's the next one? A to F. That was this one here. Actually, we can't choose that one, because if we chose that one, then we'd get the 3 cycle here. So we have to say no to this one. What about from C to F, this one here? We can't choose that one either, because then we'd have the 4 cycle here. So no to that one. Now, let's look at these over here. BE. Yep, that's fine. But then you can see we can't choose these ones with a weight 5, because this one here, that would make this 4 cycle here, and this edge here would give us this 5 cycle here, so we can't choose any of those, and in fact we are done. So BE was a yes, and the other 2 were no's. Okay, in fact, we didn't even need to consider whether we needed to add BH or BE, because if you look at the red lines here, we already have a spanning tree, so we can't actually add any more edges, because then we'd get a cycle somewhere. So we could actually have stopped right there. And the spanning tree will look like this if we look at what we have. And there we have the answer to this part of the problem. So this was only one solution. We could have found other minimal spanning trees, and in fact we have to do that according to the problem. So what could we do here? Well, we could replace some of these edges with other edges. For instance, we could say, instead of this edge here, we could choose this edge here. So instead of AB, we could have BD. This also gives us a minimal spanning tree. It's still a spanning tree, and it's minimal because we've just replaced an edge with weight 1 by an edge with weight 1, giving the same total weight. In fact, let's just find out what the weights are equal to. 4, 1, 1, that's 6. 2, 2, that's 10. 3 is 13, and 5. We get a total weight of 18. Okay, we're also asked to find how many spanning trees are there. And in general, there are some very nice results that can describe that, but in our case, it's quite simple. So if you look at the edges of weight 1, we can choose any 2 of them, but not 3. And this will still be a spanning tree. So we've got for these ones here, we have 3 possibilities. We choose 2 out of the 3. For the 2s, you see that they form a little triangle as well, so we can choose any 2 out of these 3, and that will also give us a minimal spanning tree. So here we have 3 more possibilities. Now for the ones with 3, we could either choose this one or this one. And so we have 2 choices here. And for the ones with 4, we have these ones here, but we can actually only choose this one or this one. We won't be able to choose this one because that would give a circuit either with this choice of the red ones, or if you had chosen this one or this one in your tree. So actually we can only have 2 choices here. So this demonstrates that it's not just the number of edges with 4 that we're looking at. Finally, for the edges with edge weight 5, for the same reasons we can't choose this edge, but we can choose either this edge or this edge. So we get 2 choices there. So if we see 3 choices for the edges with weight 1, 3 with weight 2, and so forth, we get 3 times 3 times 2 times 2 times 2 choices. So 3 times 3 times 2 times 2 times 2. And minimal spanning trees. And what's this equal to? 9 times 8, which is 72. Minimal spanning trees. There we go. Okay. In this part of the problem, we again have to find a spanning tree, just like in part A. But this time, we're not trying to find a minimal spanning tree. We're trying to find a spanning tree which is, okay, it's minimal, but not in the same sense as before. It's not a minimal spanning tree, but it's minimal in the sense that it shows the shortest paths from a specific vertex, which is going to be A. So when we found this spanning tree, then it will show us the ways to get from A to all of the other vertices in shortest distance possible if these numbers give us distances between vertices. So this could be the house of the mayor of the little town, and he or she can then use such a spanning tree to get everywhere else in shortest possible ways. That might be at the expense of the total cost of this spanning tree. So what we get out of this might not be a minimal spanning tree in the sense that we had before. So this is a problem that looks very similar to the first problem, but it's actually quite different. And the way that we'll solve it is also quite different. We'll use a different algorithm, now called Dijkstras algorithm. And funnily enough, Dijkstra found his algorithm in the same year as Kruskal, in 1956. But this wasn't published until about 3 years later. And as I say, it's very different. So what we do here is we start off with vertex A and we add edges, just like in Kruskal's algorithm. But this time we're doing it in such a way that the spanning tree grows from a vertex to the spanning tree, and at every step we've got a connected graph. In Kruskal's algorithm we were just adding edges and they didn't have to be connected until right at the very end. So we start with A. That's our very first tiny little graph that we're going to build up, and we're going to add some of the edges that are around A. So the edges AB, AC, AD and AF, they are incident to A, so they are the ones that we can consider as candidates for the first edge that we add. So we've got A, B, AC, AD and AF. Now, I've written some small numbers here, 1, 4, 1, 4. They are the distances along these paths. In other words, at this step it's the distances from A to B, A to D, A to F, A to C. We're going to be greedy again, but in a slightly different way from Kruskal's, namely that we're going to only choose these, one of these edges, and we're going to choose one with minimal number here, 1 and 1. So for instance, let's choose this AB. So AB. And now we've built up our graph. If we draw it here, now our graph consists of these two vertices and the edge in between. So now we have a vertex, B. And in fact, we already have one of the distances from A to another vertex, namely A to B, and the distance is 1. Of course, that's obvious from the picture, but this algorithm has now given it to us as well. For our second step, we now have to look at the edges that are touching the graph, the little graph that we have. In other words, the edges incident with A or B. So it could be AC, AD, AF, or BD, BH, or BE. So, like this. Now, we've got 1, 2, 3, 4, 5, 6 edges, as you can see, adjacent to A. The little numbers here, 4, that's this 4 here, AD, that's this number here. They looked, at least they looked in the first step to be just the edge weights, but they're not actually. They say something about the length of paths. So for instance here, in BE, there's a little 6, and the same for BH. That 6 means that if we start from A and go along this red path, and now if we added BH, for instance, then we're adding 1 plus 5. This would give us a path from A to B to H, ending in H, of length 6. So here, for instance, BH, we write 6 there to signify that path length. So that's what these numbers are. They're not edge weights anymore, they're path lengths. We're trying to find minimal paths or shortest paths. So among these numbers, we want to try to find the shortest numbers, or the smallest numbers. So AD and BD, they both give paths of length 1, so we can choose either of those. Let's just choose AD. So this will be our next edge. And now we've added D. And we see that the shortest length of a path from A to D is 1. That's a little bit trivial, but our algorithm has given this result as we wanted. Okay, now let's continue. So for the third step, we now have this graph here with 2 edges, and we have to again look at edges that are incident to this little graph that we're building up, and we want to add yet another edge and another vertex. So next edge and next vertex. So we have A to C, A to F, B to, well, not B to D, because if we tried to add this B to D edge, well, then we wouldn't be adding a new vertex. We've already found the shortest path from A to D, so we don't care about getting to D anymore, so we ignore that. So we can have B to E, B to H, and then also the edges from D to F, G, and H. Here we've written up 1, 2, 3, 4, 5, 6, 7 edges that are either incident with A, B, or D, and we've excluded B to D because we need to add a new vertex. So if you look at the numbers here, the smallest numbers are these threes here, DF and DG. So if we added this edge here, DF, we'd get a path from A to F of length 1 plus 2 is 3. So that's where that 3 comes, that's where that 3 comes from. And similarly to G, A to D to G, if we added this edge here, we'd get a path of length 3. So we have 2 paths of length 3, and all of the rest are longer. So we can either choose to add this edge or this edge. Let's just choose this edge. So DF. And now we've added the vertex F, and we know that the shortest distance from A to F is in fact 3. And here's a way to get from A to F in a shortest distance, or using just the shortest distance. So going straight from A to F was actually not the shortest way. That would have given us a distance of 4. But instead, if we go from A to D to F, we have a slightly shorter way of length 3. Let's continue, like so. So we can add these 6 edges, and if you look, then the edge that gives you a shortest path here is this one here. It gives you a path of length 3. That's if we go from A to D and we add this edge here from D to G. So we have a path of length 3 from A to G. So let's do that. Adding that path there, and we're adding this edge over here. And we're adding this vertex G over there. So now we know that we can get to G using a path of length 3. Let's continue. In this step here, we've still got this edge that we can add. We can't add this edge, we can't add this edge, we can't add this edge, but we have other edges that we can add, like so. This time we can choose either to add the edge AC or DH. So let's just add AC, and we've finally got to the vertex C here, just by going straight from A to C. Okay, we've only got 2 more steps to go to add those 2 vertices, so let's do that. Here we only have one choice. We have to add the edge D to H, and that gives us a path length 4 if we want to get from A to H. Here we go. Now we're at the final step, and we can almost not add any more edges. In fact, there are only 2 choices. There's the edge from B to E and the edge from H to E. So we have B, E, and H to E. And what's that? That's going from A to D to H to E. So 1 plus 3 plus 5 is 9. And here 6 is smaller than 9, so let's add B to E. And we have finally got 1, 2, 3, 4, 5, 6, 7 vertices added to our spanning, or to our tree, which is now a spanning tree, and it gives in fact the shortest paths from A. So from A we can go along the red lines here to get to every other vertex in the shortest possible way. And in fact the distances are also given here. 1, 1, 3, 3, 4, 4, 6. They're the distances from B, D, F, G, C, H and E. So here's the solution of taking the red edges and redrawn them like this. So this is the solution. Here's the spanning tree, which shows you how to get from A to each of the other vertices in the shortest possible way, going along the red edges. It's not the only such graph, such spanning tree. We can find other solutions than this one. That depends on the choices that we make in Dijkstras' algorithm there. Now, you might wonder, here's a spanning tree. It gives us the shortest paths, but is it actually also minimal? So what's the weight of this? 4, 1, 5, 1, 3, 2, 2. So in other words, the weight, if we add those together, is 18. If you remember from part A, the minimal weight of a spanning tree in this graph was in fact 18. So this is a minimal spanning tree. Now that's pure coincidence, that's not always the case. For instance, if we take this 4 and turn it into a 5, then we get that the weight is now 19 instead of 18. Now the minimal weight is actually still 18. Because instead of this edge, we could have chosen this edge in Kruskal's algorithm. But in Dijkstras' algorithm, this would still be a spanning tree with shortest paths from A to all of these vertices, including C, because from A to C, the shortest way is going directly from A to C along that path. So this would be an example. Here we've modified the problem 39 just a little bit, but this modification shows you that you can find a spanning tree which has shortest paths from a given vertex, which need not be a minimal spanning tree. Anyway, thank you very much.